Every image is a new discovery, and each will give humanity a view of the universe that we've never seen before.
Today represents an exciting new chapter in the exploration of our universe. This telescope is one of humanity's great engineering achievements.
The deeper you look, the less you understand should be the motto of our cosmology, especially in the presence of James Webb. The dawn of a new era in astronomy has begun as the world gets its first look at the full capabilities of the James Webb Space Telescope. In a mission more than 2 decades in the making, NASA launched the most expensive science probe ever built, a $10 billion telescope that will attempt to capture starlight from the first galaxies to be born in the fiery crucible of the Big Bang. Despite experiencing multiple delays, the Webb telescope has finally delivered the goods. However, the latest images captured by the Webb telescope are sending shockwaves through the scientific community as they call our entire understanding of galaxy formation into question.
All of a sudden we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Join us as we dig into Webb's newest images, hinting at another universe at the edge of the universe. The generally accepted understanding of the universe is this. About 14 billion years ago, the Big Bang happened. In its early seconds, the laws of physics, as we understand them, didn't apply. All that would eventually become matter burst forth in a matter of seconds. First particles, like electrons and photons, and eventually neutrons and protons, the building blocks of our atoms. Early seeds of stars, planets, and galaxies expanded out from that momentous point in time and space. It spread in such a way that the universe became highly smooth. Smoothness, on an enormous scale, just means that things within the universe are relatively evenly distributed. That is, if you were to put a cube around one section of the universe, it wouldn't be much more dense than another randomly placed cube. On a smaller scale, like between galaxies or within a solar system, matter is lumpy and filled with clusters. Physicists theorize that shortly after the Big Bang, something called inflation occurred. Essentially, what was once a tiny, packed-together universe expanded out rapidly in a fraction of a second, and it continues to expand today. Inflation is part of the current standard model of the universe, called the lambda cold dark matter, or LCDM model for short. In LCDM, the shape of the universe's trajectory looks, in some depictions, like a funnel, its wide top growing and spreading further out over time. That's one interpretation, but there are others that have arisen out of the same bits of information that scientists can actually observe and measure in real life. That is, observational astronomy. The real-life information is crucial if scientists are to use models to make actual predictions about the future of our cosmos. Theoretical astrophysics is all about educated guesses that are shaped by the few things we do know for certain. Something called the cosmic microwave background contributes to a big part of that observable information. The cosmic microwave background is made up of the traces of radiation left over from an early phase of the universe. Radio telescopes can pick it up and then translate the waves into a heat map image of sorts. This image actually shows us how the contents of the universe were distributed about 400,000 years after the Big Bang, the earliest observable snapshot of a universe devoid of stars, solar systems, and galaxies. Everything was closer together and almost uniform, except for tiny fluctuations that became the matter forming stars and galaxies. This image serves as evidence that the universe started packed together and has expanded to where it is today. We also know that the universe continues to expand and can even measure, to some degree, how fast it's doing so. The cosmic microwave background also serves to confirm that an earlier version of the universe was very hot and our era is much colder. One way to test this model is by looking at very distant galaxies, equivalent to looking back in time to the first few 100 million years after the tremendous clap that started it all. The cosmos was simpler then, its evolution easier to compare against predictions. Astronomers first tried to see the earliest structures of the universe using the Hubble telescope in 1995. Over 10 days, Hubble captured 342 exposures of an empty-looking patch of space in the Big Dipper. Astronomers were astonished by the abundance hiding in the inky dark. Hubble could see thousands of galaxies at different distances and stages of development, stretching back to much earlier times than anyone expected. Hubble would go on to find some exceedingly distant galaxies. In 2016, astronomers found its most distant one, called GNZ11, a faint smudge that they dated to 400 million years after the Big Bang. That was surprisingly early for a galaxy, but it did not cast doubt on the LCDM model, in part because the galaxy is tiny, with just 1% of the Milky Way's mass, and in part because it stood alone. But when the James Webb Space Telescope came along, our story of the universe has been thrown into disarray. NASA's $10 billion gamble, in full operation since summer 2022, has shown that galaxies formed much sooner after the Big Bang than scientists previously thought, and that some of them are unexpectedly large, absolutely brimming with stars. These findings have thrown the whole scientific community into a new reality in which their existing theories no longer apply. The earliest and most massive galaxies observed by James Webb so far stand to contradict the prevailing thinking in cosmology. That's because other researchers estimate that each galaxy is seen from between 300 and 500 million years after the Big Bang, but measures more than 10 billion times as massive as our Sun. One of the galaxies even appears to be more massive than the Milky Way, despite that our own galaxy had billions of more years to form and grow. That means if the masses are right, then we are in uncharted territory. We'll require something very new about galaxy formation, or a modification to cosmology. One of the most extreme possibilities is that the universe was expanding faster shortly after the Big Bang than we predict, which might require new forces and particles. Because we believe we understand how gas, that is atom-based matter, infalls onto these early galaxies, and how star formation feeds back and prevents future gas from falling in. There's a limit for how fast material can accrete onto these objects, and although certain physical conditions can lead to an object temporarily overcoming that limit, it shouldn't be sustainable over such long timescales. Indeed, we typically see a maximum of 10% of gas converted into stars. But for galaxies to form so fast at such a size, they also would need to be converting nearly 100% of their available gas into stars. So, while 100% conversion of gas into stars is technically right at the edge of what is theoretically possible, it's really the case that this would require something to be very different from what we expect. A lot of people immediately assert that all of standard cosmology might be wrong, and perhaps we should throw out the Big Bang as the explanation for the origin of our universe as well. They hypothesize new laws of physics, like a new early form of dark energy that existed early on, or new physical phenomena, like the universe being born with supermassive black holes, or new exotic forms of matter, like a novel, long-lived particle that decays into normal matter at relatively late cosmic times. While many people believe that the explanation is perfectly absurd, that is not the case. Remember that even before the historical launch of James Webb, a number of problems arose with our current standard model of cosmology as follows. 1. Nature of dark matter. One of the fundamental issues with the LCDM model is the nature of dark matter itself. Dark matter has not been directly observed. Its existence is inferred from gravitational effects on visible matter and the cosmic microwave background. Despite extensive searches using various detection methods, including direct detection experiments and indirect astronomical observations, the particle or particles that constitute dark matter remain unidentified. 2. Dark energy and cosmological constant. The inclusion of a cosmological constant lambda to explain the accelerated expansion of the universe is another contentious point. Originally introduced by Einstein and later discarded, lambda was revived after observational evidence suggested an accelerating universe in the late 1990s. The challenge lies in reconciling the extremely small value of lambda predicted by quantum field theory with the observed energy density of dark energy, leading to what is known as the cosmological constant problem. 3. Structure, formation, and simulations. While the LCDM model successfully predicts the large-scale structure of the universe and the distribution of galaxies, discrepancies arise on smaller scales. Simulations of structure formation sometimes overpredict the number of small satellite galaxies around larger galaxies like the Milky Way. This missing satellite problem suggests that either our understanding of dark matter is incomplete, or the simulations need additional refinement, such as including baryonic physics, ordinary matter, more accurately. 4. Cusp versus core problem. Another issue within the LCDM framework is the cusp versus core problem in the density profiles of dark matter halos. Simulations tend to predict a cuspy central density profile for dark matter halos, whereas observations of dwarf galaxies and other structures hint at a more cored profile. This discrepancy raises questions about the effects of baryonic feedback processes, such as supernovae and black hole formation, on dark matter distribution, which are not fully understood or included in current simulations. 5. Tension in Hubble constant measurements. Recent measurements of the Hubble constant, which describes the rate of expansion of the universe, have shown a persistent tension between values obtained from local measurements, using objects like Cepheid variables, and those inferred from the cosmic microwave background by the Planck satellite. This tension suggests potential shortcomings in our cosmological models, including LCDM, or the presence of systematic errors in measurements that are yet to be resolved. Beyond these specific challenges, the LCDM model also leaves unanswered some fundamental questions in cosmology. For instance, it does not explain the nature of inflation, the epoch of rapid expansion thought to have occurred shortly after the Big Bang, although inflation can be accommodated within the framework of LCDM with additional scalar fields. In addition, the singularity is also a big deal. The Standard Model gets stuck at the point before the Big Bang, because according to it, there is nothing before it. In a similar way, we don't know one-time only things that happened in history. Mathematically, the Big Bang looks like it came from an undefined state, something that isn't explained by the laws of physics under Einstein's theory of general relativity. This is also called a singularity. And to Paul Steinhardt, the professor of physics and director of the Princeton Center for Theoretical Science, co-authored a paper on this topic, a cyclic model of the universe. That's the mathematical equivalent of a red flag. We all learned in school, when you get 1/0 for an answer, you're in trouble, because that's a nonsense answer. You made a mistake. In a related problem, there's also some difficulty in reconciling the inflation theory with string theory and quantum mechanics. If the model correctly described the universe, other accepted frameworks of physics would agree with it. Instead, Steinhardt says they're at odds. When one's thinking about cosmology, you're often reaching across fields of thinking, which are quite distant, either on the astro side or on the fundamental physics side, and seeing, do they fit together? In this case, the cyclic model can help do this. A cyclic model of the universe is designed to solve some of the seemingly unsolvable problems of the Big Bang and inflation models. According to Stefan Alexander, a professor of physics at Brown University and the co-inventor of an inflation model of the universe based on string theory, it allows us to go beyond the Big Bang, but without any kind of magical philosophical issues, because time has always existed in the past. Scientists have proposed a cyclic model that could work mathematically in a few ways. Its core principles are these. The Big Bang was not the beginning of time. There was a previous phase leading up to it, with multiple cycles of contraction and expansion that repeat indefinitely. and the key period defining the shape of our universe was right before the so-called Bang. There you would find a period of slow contraction called the Big Crunch. So, instead of a beginning of time arising out of nothing, the cyclic model allows for a long period of time in the lead-up. It claims to fix the same problems as the inflationary theory did, but builds even further. For one thing, the existence of time before the Big Crunch removes the singularity problem, that undefined number. It also utilizes string theory and quantum fluctuations. Like the LCDM, a cyclic model would also account for dark energy, an unobservable force that scientists believe is behind the accelerating expansion of the universe. But in the cycle model of Paul Steinhardt with Neil Turok, things get a little more like science fiction. Two identical planes, or branes, in string theory, an object that can have any number of dimensions, come together and expand apart. We can observe the 3 dimensions of our plane, but not the extra dimensions of the other. Dark energy is both the force leading the branes into a collision, with separation between them. Expansion of the branes themselves follows, and dark energy draws them together again once they're as flat and smooth as they can become. However, other scientists aren't so sure because of some of the assumptions this model brings in from string theory. Instead, some of them prefer another cyclic model from Roger Penrose, a theoretical physicist at Oxford, who came up with what Penrose himself called an outrageous new perspective on the universe. It's hard to wrap your head around. In the distant future, our solar system and galaxy will be engulfed by black holes, which eat up all the other mass in the universe, and then after an unimaginable amount of time, only black holes will exist. Eventually, only photons exist, which have no mass and therefore no energy or frequency, according to our accepted laws of physics. Penrose explains that measurements of scale no longer apply at this stage, but the shape of the universe remains. At the moment of the Big Bang, Penrose argues that when particles are so hot and close together that they also move at almost the speed of light, they also lose their mass. This creates the same conditions at the Big Bang as the cold, distant future universe. Their scale is no longer relevant, and one can beget the other. The remote future and the Big Bang become one and the same. Ultimately, what humans can observe of our universe is limited. That's why theories of the universe are never complete. We currently have a cosmology that is a glass that is 5% full. We have no idea whether the missing 95% due to a hypothesized dark matter, hypothesized dark energy, our lack of understanding of quantum mechanics due to interactions from other dimensions, due our misunderstanding of time or other misunderstanding. Put simply, nature, the universe, is too complex to ever fully understand. But in the big picture of cosmology, there are possibly new insights that can lead to a fuller understanding of the universe and lead to a cosmology that is maybe even a glass is 25% full rather than just the 5% full of the current LCDM standard model of cosmology. We don't have to achieve an understanding of the universe that is a glass 95% full. Right now, the dozens of piece parts of cosmology are mostly correct and slowly, incrementally increasing their understanding. But the stitching together of those pieces constrains, actually cripples, scientific imagination. When that cosmological model is promoted as true and necessary for the advancement of our understanding of the universe. It took a long time for science to overcome the crippling hypotheses of the flat Earth, the Ptolemaic epicycles, the biblical age of the universe as 4,000 years, the biblical story of creation of the plants and animals, and so on. And right now, the LCDM model is crippling astronomy and physics. We do not know how long it takes for a supermassive black hole to form, but black hole astrophysicists who dive into the details have avoided publishing their results because such an answer, for instance of maybe 200 billion years, is cosmological heresy in a universe that is supposed to be only 13.8 billion years old. So, we don't know is not an honest answer. It is an evasive answer by an astrophysicist community which wishes to avoid the wrath of the politically correct cosmological community. Why are there no published calculations or estimates of the time required to form a supermassive black hole? Remember what happened to S. Chandrasekhar, the student who took on the world's top astrophysicist, the Guardian Oct 19, 2017. Basically, Chandrasekhar's and others' study of black holes was destroyed because Sir Arthur Eddington destroyed Subramanian, Chandrasekhar's career, because Eddington, the great man, decided that nature would prevent black holes. Chandrasekhar got his PhD in astronomy, but could find no job in astronomy in England. So he left black hole research, left England, and won a Nobel Prize for his work on white dwarfs in 1983. The study of black holes did not become a respectable field of study. Sir Arthur died in 1944. Epilogue: after his white dwarf study, and after the golden age of black hole research was over, Chandrasekhar began to study black holes again. This time he was mocked by the young theorist who thought that nothing new was to be discovered about black holes. A second time, Chandrasekhar proved the dominant view wrong and opened up a renaissance in black hole research. Astrophysicists dare not do ruin their careers, but estimating the time it takes for a supermassive black hole to form, based on our current knowledge. Twice, Chandrasekhar demonstrated Galileo's truth. In questions of science, the authority of 1,000 is not worth the humble reasoning of a single individual. On the other hand, as our technology rapidly advances, observations that support or detract from one model or another come more often. It's completely worth making all this speculation in this work, because we are getting to the point in which this data will arrive. One such observation could produce compelling support for either a cyclic model or confirm the more accepted inflationary theory. Because of how matter is distributed in our view of the oldest part of the universe, gravitational waves that reach us may be polarized, like light, at a particular frequency. Soon, within a few years in fact, scientists may be able to determine whether this polarization exists. If it does, it will support the inflationary model. If this polarization doesn't exist, it will undermine slow contraction, a hallmark of the cyclic model. We'll be one step closer to making sense of time and space, yet still on a journey within the cosmos that's far from over. As a quick note, besides James Webb and next-gen telescopes, CERN also plays a key role in the quest to lift the veil on the universe's secrets. Planning is well underway for the successor to the world's most powerful particle accelerator, the Large Hadron Collider, known as LHC. The new atom smasher, named the Future Circular Collider, or FCC, will dwarf the LHC in size and power. It will smash particles together with so much energy. In fact, LHC operators at CERN revealed the results of a midterm review of their FCC feasibility study to the press. The feasibility study began in 2021 and is set to conclude in 2025. The findings thus far constitute 3 years of work, with scientists and engineers from across the globe determining the placement of the new accelerator's ring, the implementation of the FCC facility, concepts for detectors and funding aspects. The FCC will run under the jurisdiction of France and Switzerland, just like the LHC currently does, but the future accelerator will stretch 90.7 kilometers, making it over 3 times the length of CERN's current particle accelerator, which is 27 kilometers long. The LHC is the largest and most powerful particle accelerator in the world. The FCC will operate in the same way as the LHC, accelerating charged particles around a loop using superconducting magnets, then smashing them together as they approach the speed of light. Scientists can probe fundamental physics by observing showers of secondary particles created when particles like protons slam together. But whereas the LHC can attain energies of around 13 tera-electron volts when operating at full power, CERN says the FCC should be able to reach energies as great as 100 tera-electron volts. Its aim is to study the properties of matter at the smallest scale and highest energy. The crowning achievement of the LHC thus far is undoubtedly the discovery of the Higgs boson, the force-carrying particle of a field called the Higgs field, which permeates the universe and dictates most other particles' masses. The breakthrough sighting of the Higgs boson by 2 LHC detectors was announced on July 4, 2012, and is credited with completing the standard model of particle physics, which is humanity's best description of the universe, its particles and their interactions on a subatomic scale. Yet, the standard model still requires some tweaking, and since 2012, scientists have been using the LHC to search for physics beyond the model to make those adjustments. Success has been limited. This search will get a boost when the LHC's high luminosity upgrade is completed, which will mean the particle accelerator can perform more collisions and offer scientists more opportunities to spot exotic physics. The two main outliers of the standard model are dark matter and dark energy. Sometimes collectively known as the dark universe, these phenomena constitute such large mysteries for scientists because dark energy accounts for around 68% of the universe's energy and matter, while dark matter accounts for around 27% of these continents. But neither can be seen because they don't interact with light, and no one has been able to pin them down through other forms of direct detection either. That means that the matter and energy we understand and can account for comprise no more than 5% of the universe's contents, and we have little idea what around 95% of the universe actually is. And probing these aspects of the universe may require smashing particles together with much more energy than the high luminosity LHC is capable of. To begin with, dark matter can't be standard matter, like the atoms that make up the stuff we see around us on an everyday basis, like stars, planets, and our bodies. Remember how it doesn't interact with light? Well, protons, neutrons, and electrons, collectively known as baryons, do. So dark matter must be something else. Currently, the only way scientists can infer the presence of dark matter is via its interaction with gravity and the effect this has on baryonic matter, and in turn, light. Dark energy is even more problematic. It's the force that scientists see driving the acceleration of the universe's expansion. It concerns a period of expansion separate from the universe's initial inflation, which was triggered by the Big Bang. After that early expansion slowed to a near halt, in a later epoch, the universe unexplainably started to expand again. This expansion rate is actually speeding up to this day, with dark energy used to account for that action. But as we've discussed, scientists don't actually know what dark energy is. To see why that is troubling, imagine pushing a child on a swing. The Big Bang is akin to your first and only push that gets the swing in motion. The swing may keep going for a short while, even without any action from you. Then it will come to a half. Then imagine that it suddenly begins motion again, despite you just standing there. And not only that, but it swings faster and faster, reaching higher and higher points. This is similar to what dark energy is doing to the very fabric of space. CERN hopes the high-energy collisions of the FCC could reveal the nature of this ongoing late-universe push and the particles that make up dark matter. However, it will be some time before this future particle accelerator is ready to embark on its investigation of the dark universe. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.